Good morning and a warm welcome, everybody, to our today's Web Seminar Wednesday. Today we have Dolphitech here. Eskil Skoglund is our presenter from Norway. So a warm welcome. And we have the exciting topic, novel Matrix-NDT technology for improved composites testing. So I'm really keen to learn more about this technology. I've talked to Ludger already several times, and he said it's a game changer. So I'm really keen on learning more about it. And with that, I don't want to talk much longer. I leave the floor to you, Eskil. Enjoy and see you later for the discussion.
Okay, thank you, Bastian. So thanks for the invite to present at the Composite United. I know we tried one time earlier, but it was crashing with another seminar, I think. So I'm going to present a new ultrasound technology today that's called Matrix Array Ultrasonic Testing. And this is a new technology that's been on the market for approximately 10 years now. We say new, but in NDT market, that's quite new. And we started doing our testing in our market in composite inspection for several reasons, but that's one of the key markets that we are in, and we plan to keep that market segment. And there's many things that makes our technology fit the composites inspection quite well. So since this is a composite group, I'm going to focus on this, but hopefully I'm going to teach you a little bit about ultrasound as well. So my name is Eskil Skoglund. I'm the Chief Research Officer for Dolphitech. I like to call myself Patient Zero, as I am the technical founder of the company. And then with me, I have Ludger Epping, who is the sales manager in the DACH region. So I'm going to do a demo, and I'm going to do some application examples, but a little bit about what stands apart from our technology compared to others. So it's fast to use. It's easy to set up. Very quickly out in the field, you can get it up and running within 60 seconds. The results that you get are very easy to interpret, and it's easy to apply the equipment on your aircraft, your spaceship, or other composite part. And we have a lot of data. So this gives a lot of opportunity for advanced inspection as well, as I'll show you later. With this combined together, it's highly cost effective. So for example, we sell to airlines, and we have one airline that said that they bought 7 systems, and then they said that after one inspection, they saved the cost of these 7 systems because they can turn the aircraft around within an hour instead of 3 days, because it's easy to use. So everyone on the shift knew how to use the equipment, and they could determine that there was no damage. And it's very portable. So whether you're doing in manufacturing or out in the field, it's very easy to use. You can put it on you with a harness and climb up on your aircraft or whatever. So to dig into the technology here, or the basics, I've put on some ultrasound transducer basics here. I'm sure some of you are familiar with ultrasound, but this is how an ultrasound element works. So you have what you use ultrasound to send into your material, and then is reflected, and then you use this reflection signal to determine whether there's a damage or not. So a transducer element consists of a piezoelectric material in the middle, and that's the secret sauce here. So the piezoelectric material vibrates when it's put under voltage pressure, and also vibrates when it detects mechanical stress, which is a sound wave, for example. So the way to get a transducer to work is that you send in a high voltage pulse on transmit here. So this is a conductive layer. And then you have a conductive layer under the piezoelectric material, which is grounded. So let's say you send a 100-volt pulse in here, and then you're making a potential difference between the top electrode and the bottom electrode. And then this piezoelectric material starts to vibrate. And this vibration causes this sound. It's kind of like a speaker. When you put some electricity on a speaker, it also starts to vibrate and sends out a sound that you can hear. And depending on the thickness of this and so on, that depends the frequency. So the sound goes through this delay line, which the job is to couple the sound into the material they're inspecting. So you're absorbing the sound and sending it into your material. And the backing here that you see on the top, the gray, is meant to just absorb the sound and then kill it. So when the sound hits this, hits the part that you're inspecting, and then hits the back wall of it or a crack, it goes back through the delay line and into the piezoelectric material. And then again, the piezoelectric material starts to vibrate. And in the meantime, you will have the switch here turned from transmit to receive. And this vibration in the piezoelectric material creates a small, tiny charge on the top conductive layer. And this is what you use to make your signal that you're using to inspect. So to take you through to our technology, which is on the right here, I have to take you through the journey that we've seen the last century. So the beginning of the century, or the 1900s, then they were still using this one element transducer, which is what I showed you in the previous slide. So then you put this transducer on a material that you're inspecting, and then you send the sound into the material and get a reflection. So either you get a reflection from the back wall, as you see on the left side here, or you get a reflection, for example, from a crack or another void or damage. So that results in what we call an A scan. So you get a small echo here, a penetration echo in the beginning, and then here you see a larger echo in the back wall. So this is the pulse of that acoustic wave that you sent out. So if you hit the back wall here, then maybe your A scan is located here. But if you hit the crack, then the A scan comes earlier. And then you can see that you have some sort of object that is preventing the sound to travel through your medium. And that's what you use to inspect. And for example, to inspect on an aircraft, you need 3,000 hours of training to be able to use this kind of technology. And it's kind of old technology. It's still very much used today, but it requires more expertise to use it. Then a few decades ago, 60s, 70s, people started using what we call phased array or 1D array. And this was really introduced to the market in the late 90s, maybe early 2000s, where they put a lot of these transducer elements next to each other. So you can imagine this transducer on the left here, you put many of them next to each other. Of course, they're a little bit smaller. And then you get many, many A scans in a row. And if you flip these A scans, if you look at this A scan and flip it and put it next to each other here, as in a B scan, this is a B scan of 128 A scans. And then you can say that a high value of the A scan gives you a white color, and a low value gives you a black color. And then all of a sudden you have a cross section. So this is easier to interpret. It's a slice through material, and you can easily see where the cracks are and so on. So the next step, what we've done is that we've done a 2D array. So we have elements in both directions, both X and Y. So we're introducing another dimension. And then in addition to the A scan and the B scan, which I will show you later, we now have what we call a C scan, which is a cross section the other way in the planar field. So that makes it incredibly intuitive. It's kind of like looking through your transducer, and you can see this X-ray, similar to X-ray picture. And it's much more intuitive to interpret. So that's the travel through basic UT to phased array UT, which is a 1D array, and then to our 2D array. So let's get into the demo right away now. So our equipment, which I will not show you in video, but it has a tough pad or a tablet that comes with it. and you have the transducer module here. So this is the secret sauce. Just to show you, behind the tablet, we have what we call a black box, which is this gray box here that does some processing and has a battery and stuff like that. So showing you the screen here now, you should all be able to see my transducer module. So as I explained, I have 128 elements this way, 128 elements this way. So this is 16,384 elements on this this piece here. And then what I'm going to inspect today, this is actually a piece from an Airbus A350. So this is a 4.5 millimeter piece of a composite, and it's very, very strong, but also very light. It's very strong in this direction, but what has happened to this one, we've put out impact damage on it to make this break inside. But as you can see, you can't really see it on the outside. Now this is worn out a little bit because I've used it for 10 years to inspect, but very strong, very light material. So you need a little bit of water to start inspecting. And if I start inspecting here now, I can actually, to confuse you even more, I'm gonna put on all the pictures at the same time here. Oops. So moving this a little bit out of the way. So what you have here now is that you can kind of see I'm moving this around now, and you see the feedback I get is quite good. So starting easily here now, I'm holding it over a area with no damage, right? So I can move this cursor around these two C scans here. I can move the cursor around, and you will see the A scan is moving depending on where I have my cursor. And the C scan that you have here, we have a C scan amplitude and a C scan time of flight. This C scan amplitude are values based on the amplitude of this pulse. So you see here, this amplitude is around 50%. And then where I've clicked here is somewhat gray, a little bit light. That's 50% on this scale here. So I have a gray scale here from 0 to 100%. And the color displayed on actually that point is 50%. If I click on a little bit of a lighter area, you see that this one is, I can actually enable that so you can see it. Oh, the threshold is, well, not for now anyways, but it's almost 80%, and then that's the color up here. It's almost white. Likewise, this pulse here also have a time, which is translated into depth. So you can see this time here is about between 5 and 5.5 millimeter. And that's also this color scale here, which is the blue one. It's the 5. So this, I love this blue picture because that's a time of flight. It tells you something about the depth. And then where I slice this image is where I get my B scan here vertically along this side, and we have a B scan horizontally across this side. I'll show you the 3D afterwards. But imagine that you have set this up at United Airlines or another aircraft, and you say, if it's blue, if this picture here is blue, then everything is okay. But if I move it over to a damage, like here, if you get colors in your image, then you have a damage. So you can see this one here, both in 3D, C-scan time of flight, and also amplitude, right? So imagine just having the B-scan to look at, which is okay. It gives you quite a bit of information compared to the A-scan. And then if I go to time of flight only, which is this blue one here. So blue, everything is fine. Colors, you have damages. And in this case, I can enable the depth here. I can see that this part here is 1.69 millimeter. This is 1.96 and so on, 3.7, and the back wall here is 5.3. So what has happened here, is that this has been impacted, and then you're pushing down you're pushing down the carbon fiber and then it releases back up. But then the adhesive has released, so you have actually air pockets inside there. It's what we call an impact damage. So this must be repaired. And as you can see 90 degrees or 45 degrees on top of each other. Each layer of carbon fiber has kind of break, and that's why you see this pattern. So the ones of you that are familiar with composite production and how composite or carbon fiber is built up, this is what you see. So very easy to use. I'm okay on time here now. I have 10, 15 more minutes. But a couple of more use cases. This is what I showed you already with the A scan, B scan vertical, B scan horizontal, the 2C scans amplitude and time of flight. And now we're going to show you some examples. Our main industries are actually space and aerospace, and we also do wind energy, we do marine, and defense is also a big market that we operate in. Here's an example from FAA sample, Federal Aviation Administration from United States. And this has several inserts and several damage fabricated into it just to kind of demonstrate how this can be used. So we have pillow inserts, we have missing sealant, we have pre-correct backing, we have some extra grease down here on the left here. And then you can see here on the left side is the amplitude image, which I showed you, which is more similar to X-ray, if you will. And then you have time of flight, which is the depth information here on the right. And you can see the stringers here in blue. You can see that there's a little bit coming loose from the stringer, between the stringer and the carbon fiber, which is glued to the carbon fiber. And you can see if there are some contamination inside the part. So aerospace is maybe our biggest commercial market in addition to space. Here's another aerospace airline accident that happened. They drove this ladder into the fuselage, and it created, or they suspected it created a delamination. And as you can see from the impact damage or the damage down here, you have a huge delamination or impact damage here on the oval red one here. But you could also see that one of these stringers kind of detached a little bit, and you have a delamination from this stringer, dark blue. So the dark blue is a little bit thicker, but then you see that the glue came loose a little bit here. This is, of course, a stitched image, which is a little bit larger, a lot larger than the transducer itself. So, of course, you can inspect larger areas as well. Here's an example of a curved part. So we have several transducers with several delay lines. This is a little bit of soft delay line. That's why you can put it on a curved edge here. And you see there's a couple of inserts here actually. And this curved piece to see if there's, we inspected here. And the blue is the back wall, so everything is healthy. And the red here are damages or inserts. Now, one that's quite interesting for this group is the porosity detection in composites. And that this is since we have so much data, this gives a tremendous opportunity to inspect porosity. Not just like a spot check of porosity, but you have to remember we have 16,384 measurement points within this transducer front here. So you can get a lot of, see the variation of transducer as well. So what we did here is that we had someone produce something composite with 50% vacuum, 75% vacuum, and a 100% vacuum. There are different autoclave machines out there. There's different vacuum machines there. You have autoclave production, which is cheaper and more affordable. You have resin transmit or resin fusion methods. And all of this gives you different quality carbon fiber with different different amounts of porosity. Some have a lot of local porosity, some have evenly spread porosity, and so on. And here showing you how we set this up. So you can set it up with some requirements. So you can, for example, set on the back wall, calibrate it with a perfectly healthy, good 100% vacuum sample and said, we will approve everything that is between 40% and 80 or 100% back wall reflection, right? And then everything under that we set as pink, so it will be very easy to detect. And that's what we've done here. So you can see the 75% vacuum has a lot more pink, and you know that that's bad and not approved. And 50% vacuum, you have a lot more pink, which is even worse. But notice that you can see a lot of the variations of the porosity, not just that this is... Imagine you had a single element probe and you just get one number here. If you hit this area here that is gray, you might get an approved value. But as you can see all the variations here, you have a lot more data. And you can say that you can approve 30% pink inside that square, for example. So point here is to demonstrate, yes, it's an easy to use tool and a technology, but with all this data, we also have a lot of advanced features that is possible. Another feature that I wanted to tell you about is Matrix TTU. So we have something called through transmission. Through transmission ultrasound, which is quite easy to use. As you can see here, that's when you put two transducers next to each other. And this is easy because you have a footprint that is about 32 by 32 millimeters. And to find this on each side of a composite is easier than a probe, right? So a probe, you have a one little signal and you have to look at a single element probe. You have to look for that A scan and see if the A scan is big enough and say, okay, we're aligned. And then you move along. Let's say you have two people because this piece is huge and you cannot find the other person holding the other probe. But for MXTTU, this makes this procedure much easier because if you're aligned a little bit, you can easily align the rest of the transducer. So here you see an example of a honeycomb structure that is composite honeycomb, and you can see when the bonding has released on either side of this sandwich structure. If you look at the further one where we have stitched together an image, this is actually inserts put into a honeycomb structure, and you can see these black areas where there is no adhesion between the honeycomb and the carbon fiber. So very powerful tool where you cannot use simple pulse echo. One of the last ones I'll show you is a bonding structure. So carbon fiber bonded to carbon fiber or carbon fiber bonded to anything else is also very easy to detect here. And depending on the speed of sound and the other material, you can also measure the thickness of the part behind the transducer, but you can measure this both from the carbon fiber part or from the metal part. And you can see on the amplitude C-scan and the C-scan time of flight how this is detected. Composites can also be glass fiber. I'm guessing most of the guys here are more into carbon fiber, but that's a guess. But you have glass fiber as a growing industry as well, especially for wind blade. There are more and more wind blades now for or produced by carbon fiber because that's an even lighter and more higher quality material. But here's an example of the wind blade. This is a picture of someone that brought, these are rope climbers that brought our tool onto a wind blade. And this is a lab experience or lab tests of a wind blade with a spar in the center. So this is 30 to 35 millimeters thick, which is glass fiber and more attenuation, sound attenuation. So we have to go down in frequency to be able to inspect that. And as you can see, the resolution is not as good as high quality space or aerospace, but we can easily detect up to 2 inches of glass fiber as well. So just to sum it up, then our technology and tool is very easy to use, but at the same time, it can be used for a lot of statistical analysis and stuff like this for the quality of the carbon fiber. Now, I've worked with carbon fiber for 10, 15 years with this ultrasound technology. And I've seen a lot of different qualities. You can also, even using the correct frequency, you can also count the layers or how many carbon layers you have. And you can get a lot of data on the quality of your production, which I think is very interesting. Now, this can be if there's some wrinkles in your fiber, if there's porosity in your fiber, if there's cracks in your fiber. You can inspect different geometries of carbon fiber. And you can also inspect carbon fiber in combination with other material. So I'm curious, of course, I won't ask because there's a lot of people of how many of you guys have heard about this Dolphicam 2 and Matrix Array technology. As we've been around for a decade, but you know, these NDT is not most commercial industry, and it takes time to get accepted with rules and regulations and so on. That was a pretty quick presentation, but I will pause there to have some room for questions and follow-up. Just some information here. Again, my name is Eskil Skoglund, and my email here is here, and my phone number is here. And Ludger Epping is also our sales manager. I have the email there, and also his phone number. So you can reach out to us if you have more questions. You can also contact support@dolphitech.com if you have questions, if you want to have more ask more about the technology and so on. But that was quick, Bastian, but I hope it wasn't too short, but I'll leave some room for questions then.
No, I think perfect timing. Thank you very much, Eskil, for this very interesting presentation. And I really like the hands-on demo that you gave and the live image that we could see.